So coming back to the vectors, there are some vectors that are more important than others for different reasons. You know, the same thing is the case for numbers, right? Pi and e and 0 and 1 are more important than 7. And the same applies to vectors. So here we have some vector u, and if this vector u has length 1, then we call it a unit vector. Then we have a theorem which tells us that if we have a non-zero vector, so in other words, if we have a vector where the direction is well defined in some sense, then we can find a unit vector pointing in the same direction by just taking w and divide it by the length of v. It should be clear that if you take a vector of length of a certain length and then scale it by the inverse of that length, you get something of length 1. And the nice thing is that you then again also get something pointing in the same direction. So that's what you see here, right? I have a vector w, I have the vector w divided by w, which is a unit vector, so you can see that it always has length 1, even if my w is shorter, right? But what happens if I put it equal to 0? Then it's not defined, right? The unit vector, because this doesn't point in a particular direction. Then we have some other important vectors. They're called the standard basis vectors, and in your book, the notation is I and j, and when we get to 3 dimensions, we will have I, j, and k. And basically, these vectors are just vectors where you have I has component 1 being 1, the rest 0. Vector j has component 2 being 1, the other 0. The reason why I say the other is when you go to 3 dimensions, it's natural that you would say the others, because there would be more. And clearly these are unit vectors, right? The length of this is clearly 1. If you square 1, add 0 squared, and take the square root, you end up with 1. And one might think, why are these important? They are important because everything can be written out in terms of scalar multiplication and addition with these standard basis vectors. So if we have some vector u having component u1 and u2, we can write this as u1 times I vector plus u2 times j vector. Right? You should try writing it out. You can also think of this example. If we have 4, 2, then we say 4 times I. 4 times I would be 4 times this vector, right? What happens? 4 times 1 is 4. 4 times 0 is 0, right? So this is 4, 0. Then you take j and you multiply it by 2. Then you get 2 times 0 is 0. 2 times 1 is 2. So you have a vector 0, 2. So 4, 0 plus 0, 2 is obviously 4, 2. So you can also see it down here, right? I can make any vector by moving this blue dot, right? And what you see is you just take the coordinates of my new vector here, and then you just plug in the numbers up here. And you can see that scaling my I vector by 4, or my j vector by 2, gives you these, and adding these two up, you get the blue dot.